In your basic finite element course, you might have come across weak forms, and you might also have derived the finite element governing equations from the weak forms. You have done this for linear problems. Now, for nonlinear problems, the derivation of weak forms and their handling is a much more involved process, as is the derivation of the governing finite element equations. So we will spend some time learning how to do that for nonlinear problems. Now, the first concept that we need to learn is the concept of a variation of a function. So the variation, you can take variation of a vector, scalar, or a tensor function of let's say position. Let's start with position. So let's take a vector function ux, which is a function of x1, x2, and x3. And then you have a function u star x, which is infinitesimally different. So at every point x, u star x is very close to ux, but is not exactly ux. So u star x minus ux is the variation in u, which itself is a function of x. Now this is different from du, which represents a change in the functional value as you change dx. So if you change dx, du is the change in the functional value. That is the ordinary differential that you already know about. Contrary to that, the variation is itself a function. So du is actually a number. Du is a number. Given dx, you can find du. So du is a number, whereas delta ux, the very first variation of u, is itself a function. And in fact, if you change the independent variable, the variation of delta x will always be equal to 0. There's no variation in delta x possible. You can only vary the dependent variable, which is ux. Now, uh, how do we visualize this first variation? You can visualize the first variation as an error. You can visualize ux as the correct function, a correct solution to some problem, u star as the approximate solution, and del u as an error. You can think of it as a perturbation to the correct solution. It's for the time being, just consider it to be a function which is infinitesimally close, is very close to the actual function that you need to find, that is ux, but not exactly so. And at each and every point, there is a difference between u star and ux. Okay, so in fact, the differential operator du and delta u are commutative. So we have these two relations, that ddx of delta u is, you can take the d inside, so du dx, delta of du dx. So the derivative of the variation of a function is equal to variation of the derivative. Similarly, the integral derivative of the integral of a function is same as the integral of the derivative. Okay, so the idea of a derivative, idea of a variational, idea of a first variation, we will expand it a little bit. But before that, let me remind you of the concept of directional derivative, which I guess you all are already familiar with. Now, just to remind you of the concept of directional derivative, I found this very nice applet on the web. So here what you have is a function of two variables, a scalar function of two variables, x and y, and it's plotted in the three-dimensional space. So the heights are the value of the function fxy. So z is equal to fxy, and what you see on the left is actual 3D plot of the function. So these mountains and valleys are the 3D plot of the function, whereas on the right you see what is known as a contour plot or an iso level plot, where each of these curves here, for example, this curve here, this curve is at a constant z from the horizontal, and this curve is plotted as this curve. So these iso level curves give a two-dimensional representation of this function f(x, y). So now the directional derivative of uh, this function f in the direction of a vector u, where u is denoted by this green arrow, uh, is the gradient of u dotted with the direction u. I guess you probably know that already. So I can keep changing this u, changing the direction of this u, and you will see that this directional derivative also keeps on changing because the direction is changing, though the gradient at this point, the gradient of f at this point is one has one value. So this is just to remind you about the directional derivative. Now we will use the concept of directional derivative in a more general way to generalize the concept of a variation of a function. Now consider a general function which can be a scalar vector or a tensor of another scalar vector or tensor. In this case, for this example, for writing this formula, what I'm using is a tensor which is a function of a vector u. Now the first variation of a is the directional derivative of a in the direction of delta u, and itself is a function of u as well as delta u. So to get the first variation, you need to supply the function u, which is a function which can be a function of, let's say, x, y, z, as well as the function delta u, in which direction you want the directional derivative to be evaluated. The formula is this. We will be using it quite a bit. So you input into a slightly different function than u. The slightness is determined by this epsilon, which is a small number. So you multiply delta u, the variation, the first variation of u, with epsilon and add it to u to get a slightly perturbed function, which is slightly different from the function u, and then take the derivative del dd epsilon as epsilon tends to 0 to get the directional derivative of a in the direction of delta u. So this is how the first variation is defined as. Now, for a general, in general, this is like your generalized Taylor series. So here's a function f, which is a function of another variable x, which can be a vector, scalar, and tensor. F can be a vector, scalar, and tensor. And then f evaluated at x plus u, slightly away from x, is fx plus the derivative of directional derivative of f with respect to x in the direction of u. So that is going to be denoted by this symbol. So this subscript tells you the directional derivative is with respect to x, and this thing inside the square brackets tells you that the directional derivative is in the direction of u. So this quantity here would be called directional derivative with respect to u of a in the direction of delta u. So this symbol will give you the first variation of a. You can extend this to get the second variation. So the second variation of a would obviously be the variation of the first variation of a, and will be given by the same formula. So delta of a is given by this formula. So delta of delta a would be given by dd epsilon tending to 0 of delta a evaluated at u plus epsilon delta u. So this is the second variation of the function a. You can use this. We will do some problems now. We can use this formula to get in a very general way first variations and later second variations also of a function, any function of any scalar tensor or vector function of another scalar tensor or vector.